So you said 0.6.
Yeah. Number 13.
.6, number 13. The balancing one?
Yeah.
Okay.
I don't understand how, like, the sulfate, like, how there's only one sulfate on one side and then there are two on the product side.
Let's see what's going on. So in this case, we've got, yeah, that's fine. The sulfate is showing up in multiple compounds at once, right? So I've got fiddlesticks. I got one sulfate on my reactant side in the H2SO4. And I've got sulfate in magnesium sulfate and an ammonium sulfate. Oh, this isn't balanced at all.
Yeah, I didn't have the 2. I just had the 4 and a 3.
What craziness was I doing? It's wrong. So 4, 3. Yeah, you don't need this too. He's wrong. I made a mistake.
But I still don't understand, like, why there's 2 sulfates on the product side.
So this reaction doesn't necessarily fit any of the patterns that we know how things work out.
Oh.
So the unfortunate thing is we lie to you a lot and simplify some things. And so when we say that there's, those 5 or 6 different categories of types of reactions, not everything fits into those categories.
Okay.
So this is definitely when I would never expect you to be able to know what the products would be, but we should still be able to balance it.
Okay.
Yep.
Can we go over one from the quiz?
Sure.
It was the one that was like the lab that we did, but I still couldn't figure it out. Like, I got to a certain point, and then I just didn't know what to do from there.
Okay. Let's see if I can pull this up. Give me a sec. I have so many windows open on my computer right now. It is ridiculous. All right, how do I want to do this? Let's do it this way. All right. So here's our question. Is this the one you were talking about?
Yes.
Okay. I don't think I'm going to be able to draw on this. Are you going to let me draw? No, of course not. So we know that we've got this mystery MCl dissolving in enough water. The student then mixes that solution with excess silver nitrate, causing the AgCl to precipitate. The student collects the precipitate, dries it, and records the data. So we know what reaction is going on. So we should probably write that down. I'm going to flip back and forth. It's going to be annoying. I apologize. So we've got this mystery MCl.
I have it pulled up too, so if you just want the numbers, I can give them to you.
That would be great. So MgCl is mixing with AgNO3.
Yeah.
Okay. So it says it makes AgCl. And then that M and that NO3 are going to be able to come together. And they specifically said that these were aqueous solutions. I don't know if this is going to matter or not, but let's do it anyway. AgCl is the solid that we collect. Since this has nitrate in it, it's going to be aqueous also. So they initially tell us how many grams of MCl we put in.
It's 0.74.
So we start with 0.74 grams of the MCl. And then the AgCl, the filter paper.
Yeah, when you subtract it, it's 1.43.
So if we
That's
take
without the filter paper, yeah.
the AgCl plus the filter paper
That's
minus the filter.
Yeah. It should be 1.43.
1.43. Are we okay up to that point?
Yes.
Okay. So now, the only real way to identify what this is to find out what its molar mass is. And we can't just add up its molar mass because we don't know what M is. But molar mass is always grams divided by moles. So if I can figure out how many grams of MCl I have and divided by the number of moles of MCl I have, that'll give me my molar mass. So the grams of MCl, I've got that part already. But I don't know my moles of MCl. But I can do some stoichiometry to figure it out. So my equation is balanced the way it is right now. If I have 1.43 grams of AgCl, anytime you've got grams, you should always be able to turn it into moles.
Right.
And they even tell us in the problem what the molar mass of AgCl is. Right?
It's 143. Yeah.
143 point something, right?
That's just what it says.
Just 143, okay. I was thinking of a different problem. And then I can look and do a stoichiometric ratio, do my mole ratio, and say, well, 1 mole of AgCl is formed from every 1 mole of our mystery chloride. And so since this is multiple choice question, technically no calculator. So 1.43 divided by 143 is 0.01. So now I've got my grams of MCl and I've got my moles of MCl. So if I take 0.74 grams divided by 0.01 moles, that gives me 74 grams per mole. So that's the molar mass of my whole compound of MCl. I know that chlorine has a molar mass of, it's like about 35.5, 35.45. So if I subtract that, I get, was that 38.5?
Yeah.
So if I look at what my choices are for that problem, the positive ion that's closest to that is potassium.
Okay, and it wouldn't be argon because that's not a metal.
Yeah, argon can't, it's not gonna be able to bond there.
Okay. Thank you.
You're welcome.
Wait, Miss Blasky, for that question. So you would have to use AgCl to get MCl.
Yep, because this is the only thing we actually know anything about.
So they have to give us that for us to get the unknown metal.
Yep. So this is the whole reason why this process is used to help identify unknowns. Because if we can make a solid that we can actually collect, we can work the mole ratios backwards to figure out what we've got.
Okay, I think this makes sense. Thank you.
I have a question. Oh, go ahead.
Okay, thank you. Could you work through the empirical formula question in the back of our packets? It's the second number 4.
Yeah. Second number 4. All right. This is the one that says a chemist needs to determine the empirical formula.
Yeah.
Okay. Aha. All right. I was trying to figure out how to flip it because my answer key was sideways. So this is going to be really similar to the mastering chemistry question that we just went over. So it says we've got a compound that's got carbon, hydrogen, nitrogen, and oxygen. We burn it in excess oxygen and it makes carbon dioxide and hydrogen. And I put plus dot, dot, dot because we've got to take care of that nitrogen somewhere. They're just not telling us about it. So it's not super desperately important because they're going to tell us all the information we need to know. It says specifically the reaction produced 6.8618 grams of carbon dioxide and 1.7557 grams of water. So just like the problem that Julian asked about, excuse me, we can start with the grams of carbon dioxide that they gave us. Turn that into moles because we always want to turn everything into moles. Use that same ratio to say that every mole, any carbon that shows up in that carbon dioxide had to come from our initial product or initial reactant. So every mole of carbon dioxide's got 1 mole of carbon in it. Now this time it wants the mass in grams. So we need to go one extra step and say, well, for every mole of carbon, it's going to have a mass of 12.01 grams. So that's going to tell us the mass of carbon that came from that original sample, since all of that carbon ended up in our carbon dioxide. And then in B, doing the same thing for the hydrogen. Same thing, we start with the mass of hydrogen, we convert it into moles, or the mass of water, convert it into moles of water. Every mole of hydrogen has, I can't speak tonight. Every mole of water has 2 moles of hydrogen. And then again, to get that back to grams, now we're just talking about individual hydrogens and not the water. So the mass is 1.008, and that'll give us the mass of hydrogen. See, they're sort of giving us the information about the nitrogen. If it's 14.14% of the whole thing, we take the decimal version of that percentage times the mass of the whole compound. That gives us our grams of nitrogen. So now we have grams of carbon, grams of hydrogen, grams of nitrogen, and we know the mass of the whole compound put together. So if we subtract that away, whatever remains has to be the mass of oxygen. So then E is just asking us to do like a good old-fashioned empirical formula now. We've got the masses of each of our elements. I didn't have room to show this all out, but if I know how many grams of oxygen I have, I can turn that grams of oxygen into moles of oxygen. If I know how many grams of nitrogen I have, I turn grams into moles. Same thing with the grams of hydrogen, turning it into moles, and grams of carbon, turning it into moles. I divide all of those by the smallest, which is the nitrogen. So I'm going to divide everything by 0.03898. 0.03898. 0.03898. 0.03898. Divided by the smallest gives me that whole number ratio. Gives me C4H5NO2. So that's a long problem, right? That's a lot of stoichiometry in one problem to try and figure out what's going on. But it's still just a little bit of stoichiometry, well, a lot of stoichiometry, and then an empirical formula problem. Is that okay, Keenan?
Yeah, thank you.
Okay. Jinyu, did you have a question?
Yeah, I wanted to review 2 other questions on the quiz.
Okay.
One of them was, I don't remember it, but it showed them dissociating, I think.
Yeah. Yeah. Here we go. The reaction between sodium and water.
Yeah.
Is that the one? Okay. So this is a single replacement reaction instead of a double replacement reaction. So far, we've mostly done net ionic equations for double replacement, but it still is going to work out the same way. If I have solid sodium, nothing can change about that. If I have water, that's liquid water, so that has to stay a liquid. So A is going to be out because they took that water and broke it up into ions and said it was an aqueous solution. Water can't dissolve in itself. So A is out. Looking at B, C, and D now, I got to think about how this is going to react. Sodium can make a positive ion. So if it's going to bond with anything, it has to bond with a negative ion. So C is going to be out. NaH. NaH does exist, but it's not going to come out of this reaction. And because if you look at C, the oxygen disappeared. There's no oxygen on the product side. And so that's not possible. So then I'm looking at these two, and this comes down to solubility. Anything with sodium in it is going to be an aqueous solution. It's not going to be a solid. So that means that B has to be our answer.
Yeah, I just use like process of elimination for that one because
And that's
I
totally fine.
realized that A and C, they didn't have oxygens on the other, well, no, C didn't have oxygen on the other side. And then D, I saw that there were like there were 3 like hydrogen ions and there's only 2 on the other side. I don't know how my brain was working during that question, but I just guessed.
Process of elimination is a totally fine thing to do for multiple choice. Sometimes I think we'll get to see some problems where I think it's probably the only way to actually solve a problem without spending an hour on it.
And then yeah, the other question I had was the very last question, number 5.
Well, my 5 might be different because I think they got shuffled.
Oh no, it is the 5. So.
This one 5? Okay.
Yeah.
So this is a sort of a stoichiometry mole ratio kind of question. So if I initially start with 2 moles of F2, and then I reduce it down to 1, I have half of my reactant available to me now. So if I have half of the reactant, I'm also going to end up with half of my products, because it tells me that I have excess of sodium hydroxide, so that's not going to influence my reaction.
I was trying to do like stoichiometry for it, and
I mean, you
just
could,
don't-
so you could write out a stoich for it. Like you could say, so you say I have 2 moles of F2, and the mole ratio says 2 moles of F2 make 1 mole of OF2. And so that would be 1. And then you could say, well, instead of 2 moles of F2, I now have 1 mole of F2. It's the same mole ratio because it's the same equation. And that would only be half a mole of OF2. So the math supports it also.
Yeah, again, I didn't know what I was doing during that question, because somehow I didn't end up with that when I was doing stoic.
Yeah.
Can you please go over in the back of the packet free response question number 6?
Free response question number 6. Is that the barium hydroxide one?
Yes.
Okay. All right. So again, I would this is sort of in the style of an AP style free response question, because it's got all the different parts that all relate back and forth. This is similar to those ones where you have to find out what the mystery metal is. Only instead of finding a mystery metal, we're trying to figure out how much water is attached to that hydrate. So we talked about these formulas, that dot means that this barium hydroxide molecule is surrounded by water atoms or water molecules. We just need to figure out how many. So just like we did before, we've got some data here. You've got the mass of a clean, dry crucible. We put the mass of the crucible plus our unknown hydrate compound in, and then you heat it up a whole bunch of times until the mass stops changing, and we find the mass of, no, this one is different. This one we react it. Okay, so we react that with sodium sulfate solution. We heat it up, and that gives us the mass of the barium sulfate that we made. Do they give us an equation? No, we have to write it. Okay. So in part A, says calculate the mass of the hydrate sample that was there before heating. So again, all we have to do, not all, what we need to do is we need to subtract away the mass of that crucible to find out just how much barium hydroxide hydrate there was. So if we do that, we get 4.224 grams. And then B says to write a balanced equation. So the barium hydroxide is just barium hydroxide now. It doesn't have that dot water on it because we heated it up and drove that water off. That dried barium hydroxide is going to react with sodium sulfate. And so this is a good old-fashioned double replacement reaction. So the barium is going to end up with the sulfate. The sodium is going to end up with the hydroxide. Based on solubility rules, sodium hydroxide is going to be aqueous and the barium sulfate is going to be solid. They even told us in the problem that we collect that precipitate of barium sulfate. Make sure we balance it, so we got to put a 2 in front of that sodium hydroxide. So then C, the mass of the white precipitate was 3.126 grams. They told us that in the data table. Calculate the number of moles of this precipitate. So all we have to do is do a molar mass. They give us the grams of barium sulfate. Use the molar mass of barium sulfate to convert that into moles. And now again, just like we did on the MCl problem, I know how many moles of barium sulfate I have. I can go back up to my balanced equation and see that they have a 1-to-1 ratio. So I can go from talking about the barium sulfate to talking about the barium hydroxide. They specifically want the mass of that barium hydroxide, so then I have to use the molar mass of barium hydroxide to get to the grams of barium hydroxide. And then E, calculate the mass of water that was lost in the heating process. Well, we calculated in A how much of that initial sample we had. We now know that 2.294 grams of that was barium hydroxide. So it means that 1.93 grams of that mass had to be the water that was driven off. So now I've got grams of barium hydroxide, I've got grams of water. I'm going to do an empirical formula problem with whole molecules instead of with elements, which is a little funky, but it's going to work out the same way because we're still trying to find that ratio. Oops. So if I have the barium hydroxide, I had 2.294 grams of the barium hydroxide. I turned that into moles. I had the 1.93 grams of water. I turned that into moles. To find the ratio, I divide by the smallest number. Gives me a ratio of 1 to 8, which means that I have 1 barium hydroxide for every 8 waters. So that tells me what that N variable is.
Okay, thank you.
You're welcome. If at any time what I'm saying doesn't make sense, stop me. Tell me I'm talking crazy.
Miss Blaschke,
Yes, sir.
can you go to page 13 real quick? And then,
Of the packet?
yes.
Okay.
If you look at example 25 and then example 28, like, I don't understand how, like, you add one extra step to the stoic and then there's one less step on example 28. Do you want to talk about where you, because like on
Okay.
25 you add a molar mass.
So what I did was, so in number 25, they specifically are asking what mass of mercury bromide.
Okay.
And so since they're giving me information about 2 reactants, I know this has to be a limiting reactant question. So I went ahead and cranked out both of my answers to grams, because then whatever I got as the smallest was going to actually be my answer. It was going to be my mass. In 28, I tried to save some time and some paper because all they want to know is what is the limiting reactant. They're not specifically asking me to go to grams or to find a mass of my product. They just wanted me to say which one is limiting my reaction. And so I stopped at moles. I'm still comparing the same thing. I'm still comparing moles of carbon dioxide to moles of carbon dioxide.
But you're relating moles.
But I left off that last step because I didn't need it.
Mm.
I mean, I could have gone 1 mole of CO2 is 44.01 grams on both of them. I still would have gotten the same answer. It just would have turned out in grams instead of moles. But I was just trying to save some time and not have to work it out all the way if I don't have to.
Gotcha. Thank you.
Miss Blaschke, for the same question, like for 26 actually,
Yeah.
when it says what mass of excess reactant remains from the question above, why'd you start in grams?
Because I went back and started with my limiting reactant. There's multiple ways to do this one. So you could have started with the 15 grams of mercury. You also could have started with the 21 grams of HGBr. But either way, you're going to work
Okay.
it back to the bromine.
Okay. Okay. I
Because either
understand.
way, we're saying, so if I used up all 15 grams of my mercury, or if I made all 21 grams of the mercury bromide, how many grams of that bromine were involved in that reaction?
Okay, that makes sense. Thank you.
If at some point in that problem I had to stop at moles, like if it had been set up like number 28 and then said, how much excess do you have? You could start with moles and just do the mole ratio. And that
Oh,
would sort it out.
okay.
It's
Yeah, I
all
think that
about
was my actual
it's all about the
question.
comparison. It's all about which element are you starting with, which with whatever data you have about that element or compound, going to whichever compound you're trying to get to, whatever information you need to find about that final compound. If they tell you, if they say how many moles, then you stop at moles. If they say how many grams, you go all the way to grams.
Okay.
Anything else?
How long is this quiz gonna be? I mean, test.
It's 10 questions.
That's all?
Yeah.
Do they have parts down to E?
They don't go down to E, no. So there's a couple write-out questions, like a couple free response-y kind of ones. Maybe it's got an A or a B. It doesn't go to an E. Like I said, this first test isn't going to look like that AP style question all the way through, just because we don't have enough time and there's
Okay.
too much to test in one day to give you like a crazy, like one of those ones we just went over in the back of the packet. There's a couple questions that are just like identifying whether something's going to be a precipitate or soluble. So like it gives you a list of chemicals and you need to identify which one would be soluble and which one would be a precipitate. There's some writing names for formulas and formulas for names.
Okay.
There's a couple multiple choice questions about picking what we talked about today in class about the particle diagrams. I think there's two multiple choice questions where you pick which particle diagram is correct for the situation that they give you. It's kind of mixed up. It's a little bit of everything.
I expected this to be a big test.
Big test comes next.
What joy.
I was gonna ask about the particle diagrams. I don't really understand like the point of them, or
so the point of them is that they're showing a representation of what's happening at the teeny tiny level. So we can show what elements are that mixture is made out of. We can show what compounds it's made out of. We can talk about whether there's limiting reactants or excess reactants left over. So we can basically see a picture of what's happening in a reaction or in a system.
so what's the triangle thing in the beginning?
So the triangle thing, this is something that we're going to use as we go through class more and more. Let me go find it. The triangle is just talking about how for pretty much any situation or any topic we talk about, there are multiple ways to explain that topic. So we get really comfortable with the symbolic method of writing out chemical equations or solving math problems. And we have some fun with the macroscopic when we get to be able to see reactions or see what happens when things mix together, but we don't focus a ton on that submicroscopic. And AP cares a lot about this corner. So basically, if we said for any chemical reaction, you should be able to represent all three of these things. You should be able to explain, what you would see. You should be able to explain it in terms of a chemical, like a balanced equation, and you should be able to explain what's happening, showing it in pictures with each particle or ion identified.
Okay. Because I thought that when you meant like draw it out, I thought you meant like filling in the triangle or something.
Oh, no.
Yeah,
It's
I
just
was
it's
confused.
drawing pictures that look like these guys. Anything else?
On page 14 of the packet, could you go over example number 32?
1432. Yeah. Okay. So this is a limiting reactant problem with a little bit of extra information. So they tell us that titanium 4 oxide, along with chlorine gas, is made by reacting titanium 4 chloride with oxygen. So we write out that equation, we balance it. It says 3.5 moles of titanium chloride react with 4.5 moles of oxygen, and 250 grams of titanium 4 oxide were produced. So that 250 grams, that's telling me in real life, somebody sat down and did this equation, and that's what they got out of it, somebody in a lab. And so when we talk about percent yield, that amount that you got out of the lab, we call this our actual measurement. So if they're giving me these two pieces of information about the reactants, that's what triggers that it needs to be a limiting reactant question to me. So I'm starting with moles, so I don't need that first grams to mole step. Convert moles of titanium chloride to grams of titanium oxide, to moles of oxygen to grams of titanium oxide, and I find that this is my limiting reactant, and so this is what we call our theoretical value. So theoretical is what the math tells us and says, in a perfect world, this is how much you could make. The actual is what actually happened in a lab. And so to find the percent yield, we take that actual value divided by the theoretical value and then multiply it by 100 to turn it into a percent to tell us how much of that theoretical value was produced in the lab.
Will you always be given an actual value?
In some way, shape, or form, yes.
So like, will there like in future reference, will there be like any question where we like you need to find like the actual, or is that not a thing?
The worst they might do to you is like give it to you in moles and you have to convert it in grams or vice versa. But that's something that would be given to you. Or really what will happen is when we start doing more lab experiments, we'll actually be doing a percent yield ourselves. And so we'll crank through the math and find out what we should get. We'll measure the mass in the lab on a balance, and then we'll be able to do that calculation. I probably look really creepy because I'm looking this direction. I have all of you on this screen and my camera is on the screen. Sorry about that. All right, probably got time for one last question, if anybody's got one.
It's a dead silence.
Nothing?
I just have a question about the test.
Okay.
Is there a percent yield question?
It's possible. Honestly, I don't remember.
Okay.
I've got a question about the test too.
Okay.
So, you know the solubility rules? Is it just SNAP, or is it like the ones we learned last year too?
SNAP is all you need to know.
Okay.
I double checked all of the questions to make sure that SNAP is the only thing you need to know.
Okay.
Those other solubility rules still exist, just College Board doesn't care that you know them. So we're not going to waste our time on them.
I also have a question about the test.
Okay.
Is it going to be timed, or do we have the entire class to do it?
You've got the whole class period.
Okay.
So I'm going to have to set a timer on the test just because there's some people who have to take it at home. But that timer is going to be 48 minutes or however long a class period is anyway.
Okay. Thank you.
Yep.
Will
Another
that
question
online
about-
test?
Go ahead, Caroline.
Will that online test be similar setup to the quiz?
I would say similar skills that you're going to have to do, but it's not going to be all multiple choice like that. So
Will
like
it
I'm
still
going
be
to
on
ask you that it's still on the computer, so you're still going to be typing in your answers, but I'm going to ask you to submit a sheet with your work on it also.
Okay.
So that
Thank you.
if you mess up something, I can still give you partial credit if you show me all of your work and everything.
Okay. Thanks.
Brenda, do you have a question?
Yeah, about the quiz. Will there be sig figs on the quiz too?
Always.
I mean,
Sig
like
figs are a part
specific
of
sig
life.
quiz.
Not specific. No, not like how many
Okay.
sig figs are in this thing.
Okay, cool.
But I would expect you to round to the correct number of sig figs when you had to do math.
And if we don't, that's points off.
If it's ridiculous, yes. If
Okay.
you're like a sig fig off at this point, I'm not super concerned about that.
Okay, thank you.
All right, y'all. It's 9 o'clock. Get a good night's sleep tonight. Take a couple of nice deep breaths. I know that there's a lot of sort of nerves about this first test, but it will be okay. All right. If you've got any last minute questions, you can send me a message. I probably won't get it answered until the morning. Or you can ask me real quickly before class starts. Sound good? Nobody has their screen on, so I can't tell if you're giving me a thumbs up or not.
Yes, it's good.
Yep. Thanks.
There you go, Lauren. Thank you. I'll see y'all tomorrow, okay?
See ya.
Bye.
Bye.